Our first example of a three-variable linear system is going to be just an introduction to the idea of solving for one variable, using that to solve for a second variable, and then using both of those to solve for the third variable. So our first system, we have 3x minus 2y plus 2z is equal to 10, negative 5y plus 6z is equal to 6, and negative 2z is equal to 8. Not all of our equations have all three variables in them. You'll notice that our first equation has x, y, and z. Second equation has just y and z, and our third equation only has one variable z. So we can actually use this equation to solve for our first variable. One of the keys to solving a three-variable system is to stay organized. So one of my strategies is to label all three of my equations and use those labels whenever I'm using those equations to solve. Here I'm taking equation 3, negative 2z is equal to 8, which we can easily solve by dividing both sides by negative 2, giving us z is equal to negative 4. Now we can use this value in our remaining equations to solve for the other variables. Since equation 2 has the variable z, which we've already solved for, and only one more variable, y, we're going to go ahead and substitute our value for z into equation 2 to solve for y. Substituting negative 4 in for z in the second equation will give us the equation negative 5y minus 24 is equal to 6. Adding 24 to both sides gives us negative 5y is equal to 30. And dividing both sides by negative 5 gives us y is equal to negative 6. Now that we know the values for both z and y, we can use them in our first equation, where we have all three variables, to solve for x. Substituting the values in, we now have the equation 3x plus 12 minus 8 is equal to 10. We can combine like terms, giving us 3x plus 4, which equals 10. Subtracting 4 from both sides gives us 3x is equal to 6. And finally, dividing by 3 on both sides gives us x is equal to 2. To go back and check to make sure that your answers are correct, you should always go back and plug in all of your values in your original equations to check that your equations end up being true. In this case, all three of our equations end up being true statements when we plug in our x, y, and z values. This is our solution to the system of equations. You could also think of it as a coordinate, as an ordered triple to negative 6 and negative 4. You can think of this as a coordinate in 3D space. Now, example 2 is where the fun really begins. In this situation, you'll notice that all three equations have all three unknowns. So we're gonna go ahead and use the elimination method to help us solve this system of equations. Now, to do this, once again, we want to stay organized. So I will be labeling my equations 1, 2, and 3. Now, later on, we will also have equations 4 and 5. And we'll get to that in just a little bit. We will have to find them and create them before we can use them. So the elimination method with a three-variable system can be summed up this way. You want to go from 3 equations with 3 variables, eliminate a variable so that you end up with 2 new equations that have 2 variables, and then you can solve that like a normal 2x2 or 2-variable system of equations by eliminating another variable to get one equation with one variable. Then you substitute that back into your previous equations to solve for the second variable, and then sub those back into one of your original equations to solve for the third variable. So we're going to use this method on the next several examples so that you can get a hang of it. Just like in a two-variable system, we want to choose a variable to eliminate from all three equations. Now we're going to have to do this twice because we need to create equations 4 and 5, which are going to be the two equations with two variables that we'll be able to solve and eliminate another variable. So we get to choose which variables we'd like to eliminate, and in this situation I'm going to go ahead and choose y, because it seems like the y variables are going to be pretty easy to eliminate through some addition and multiplication. To start off, I'm going to create equation 4 by eliminating y from two of these equations. I'm going to start off by using equation 1 and equation 2 and eliminate the y variable from these two equations to create equation number 4. Since the coefficient for y in both equations is 1, with one being positive, the other negative, I can simply add these equations together and we will eliminate the y. So negative x plus 3x gives us 2x. Y is eliminated because we have 0y. 2z plus 1z gives us 3z. And negative 3 plus negative 2 gives us negative 5. So this will be our equation 4, and we will use it a little bit later. So hang on to this equation. Now to create equation 5, I have to take another pair of these three equations and eliminate the variable y. So this time I'm going to choose 1 and 3 to make 5. Now if we were to simply add these at this moment, we would not eliminate the variable y, since our first equation has a coefficient 1 and our second equation has negative 3. So I'm going to go ahead and multiply the first equation by 3, so we get negative 3x plus 3y plus 6z is equal to negative 9. Now when we add these equations, negative 3y and positive 3y will be eliminated, and we will be left with the equation negative x plus 2z is equal to negative 8. This will be our equation number 5. So now we've gone from 3 equations with 3 variables to a system of 2 equations with 2 variables. And we can use elimination one more time to solve for our first variable and be able to substitute back up and solve our system. So we'll use elimination again to eliminate one of the variables from equations 4 and 5. The simplest course of action might be to multiply equation 5 by 2. This way we can eliminate the variable x when we add 2x plus negative 2x. 3z plus 4z gives us 7z, and negative 5 plus negative 16 is equal to negative 21. Now we can simply divide both sides of our equation by 7 to give us the value of our first variable. Z is equal to negative 3. So now we can use this value for z to substitute back into one of our 2 equations with 2 variables to solve for x. Now it doesn't matter which equation we choose from our 2 equations with 2 variables. We can choose either 4 or 5 to substitute z in to solve for x. So I'm going to go ahead and choose equation 4 and substitute negative 3 for z. So now we can go ahead and start to solve for x. 2x minus 9 would be equal to negative 5. 2x would then equal to positive 4 after adding 9 to both sides. And then x is equal to 2 after dividing both sides of the equation by 2. Now we can finally go back and substitute both of these values into one of our original 3 equations to finally solve for our last variable y. I'll go ahead and use equation 1 to substitute back in x is equal to 2 and z equal to -3 and solve for y. This gives us -2 plus y minus 6 is equal to -3. Combining like terms, y minus 8 is equal to -3. Then finally adding 8 to both sides gives us y equals 5. So we get the solution, x equals 2, y equals 5, and z equals -3, or the ordered triple 2, 5, -3. In our next example, I'm going to go ahead and eliminate z from these equations to create 4 and 5. So we're eliminating z first. To create equation 4, I will go ahead and add equations 1 and 2, since 2z and -2z will eliminate, leaving us with the equation 3x plus 2y is equal to 1. To create equation 5, I'm going to go ahead and use equations 1 and 3 to eliminate z. Of course, for equation 3, we're going to need to multiply it by positive 2 so that when we add these two equations, z can be eliminated once again, leaving us with the equation 3x plus 5y equals 7, our new equation number 5. Now we can use our two equations to eliminate one of our variables once again to find our final equation and solve for one of our variables. In this case, I will go ahead and multiply equation 5 by -1 and add together, giving us the equation -3y equals -6, which can be easily solved by dividing by -3, giving us y is equal to 2 as our first variable to be solved. Substituting y equals 2 back into equation 4, we get 3x plus 4 is equal to 1, meaning 3x is equal to -3, and finally we get x equal to -1 as the next value for a variable. Finally, we can use our two new values to solve for z. -1 plus 2 gives us 1 plus 2z, which equals to -3, which means 2z is equal to -4. And finally, after dividing by 2, we get z is equal to -2. So our solution is x equals -1, y equal to 2, z equal to -2. The order triple, -1, 2, -2. Now our next three variable system is a little bit different. In this case, each equation only has two variables. So we're not going to be able to use elimination like we did in the previous examples. However, in this case, we actually can use substitution. In our first equation, we can solve for y, giving us y equals to -4z minus 14. Our second equation can be solved for x, giving us x equals -3z minus 8. So now we have two equations solved for y and x where they are equal to an equation with, or an expression with z as the variable. And you will also notice in equation 3 we have the variables x and y, which we can now substitute with our new expressions. Now you'll notice that we have one equation with only one variable, z, which we can now solve. So using the distributive property and combining like terms gives us the equation 6z plus 26 equals 8. Subtracting 26 from both sides of the equation, then dividing both sides by 6 gives us the value z equals -3. Substituting z back into the two equations which we solved for y and x will let us easily find that y is equal to -2 and x is equal to 1. So we get the solution 1, -2, and -3 for this system. In example number 5, we have the potential of having a system of equations with either no solution or infinitely many solutions. Just as a reminder, if the system has no solution, it means that we end up with a false statement after solving one of our equations, something like 0 is equal to 5 or 1 equal to -2. These are false, so that means we would have no solution. Infinite solutions means we would probably end up with some kind of true statement, like 0 equals 0 or 5 equals 5. This would indicate that we have infinitely many solutions. Using equations 1 and 2 to eliminate the variable x, I get equation 4, y plus 2z is equal to 3. Using equations 2 and 3 to make equation 5, and also multiplying equation 2 by 2, we can eliminate x and wind up with the equation 3y plus 6z is equal to 9. We can now eliminate another variable by multiplying equation 4 by -3. So we can now add these two equations together, but what we will find is that every value gets eliminated, leaving us with 0 is equal to 0, a true statement. This means that we do have infinitely many solutions, and that by choosing either y or z, we can find an expression to represent all the different types of solutions for the other two variables. To find those expressions, we need to solve for one of our variables in terms of the other. So what we're going to do is we are going to choose y to be our variable that we're going to use, since we can choose any y value for this system to be true. So we're going to use equation 4 to solve for z in terms of y. Since 2z plus y is equal to 3, then we can say that 2z is equal to -y plus 3, and so z is equal to -1/2 y plus 3/2. Now that we've found z in terms of y, we can also do the same for x. In this case, I'm going to use equation 3 and substitute my new expression for z into this equation and use it to solve for x in terms of y. Distributing -4 into this expression gives us 2x plus 5y plus 2y minus 6 equals 11. Combining like terms gives us 2x plus 7y equals 17. And we can subtract 7y from both sides, giving us 2x is equal to -7y plus 17. Dividing everything by 2 leaves us with x equal to -7/2 y plus 17/2. Since y can be any value that we choose, our final solution will look like -7/2 y plus 17/2 for our x variable, y, and -1/2 y plus 3/2 for. Finally, we can use a 3-variable system to find the answer to this word problem. Donna, Greg, and Jose have a total of $113 in their wallets. Greg has 7 more than Donna. Jose has 3 times what Greg has. How much do they have in their wallets? So we will need to write a system of 3 equations using 3 variables to solve this problem. Now we will represent Donna's money with D, Greg's money with G, and Jose's money with J. Now if we look at the first sentence, you'll notice that all 3 have a total of $113 in their wallets. Total meaning that if we take Donna's money plus Greg's money plus Jose's money, all together they have $113. Now we also know that Greg has $7 more than Donna. So we can say that Greg's money G is equal to Donna's money D plus $7. $7 more than Donna. We also know that Jose has 3 times the money that Greg has. So J, Jose's money, is equal to 3 times Greg, 3G. Since we know what G equals and what J is equal to, we can substitute these both for G and J in the first equation and use that to solve for D. So we can, if we substitute into our first equation, we get D plus 7 plus 3G is equal to 113. The only problem is that we want to have one equation with just one variable, and here we have 2 variables, D and G. However, since we know the value of G and J is equal to 3 times G, then we can rewrite J as 3 times D plus 7. Substituting this new value for J gives us one equation with just one variable. Now we can go ahead and start to solve. So after distributing 3, combining like terms, we get 5D plus 28 is equal to 113. Subtracting 28 and dividing by 5 lets us know that Donna had $17 in her wallet. Since we know that Greg had $7 more than Donna, we know that Greg's money is equal to 17 plus 7, which is $24 in his wallet. And since Jose had 3 times what Greg did in his wallet, we know that Jose had a grand total of $72 in his wallet. And we can even check, and yes indeed, 17 plus 24 plus 72 means that altogether they had $113 in their wallets.